Hello everyone, my name is Vaidishwari Chandradas. I am going to present about example 1. This is full coding for example 1. Here we plot a generated analog signal as a input signal. And then from the signal we cannot plot simple signal, so we encode and decode the signal, and also we plot square signal. This expression shows the time meter from 0 to 3 with the time interval 0.01. Then we make sine wave by using parameter 2 times pi times time. Then this expression shows the square wave by using 2 times pi times 10 times time. And this shows the square is equal or less to 0. Next we make sample signal by using A represent for sine wave, which dot product times, and P represents square wave. These codings for plot the graph, we plot analog signal and then we supply all, and then we plot T against sine wave and X label as time and Y label as amplitude. Then here we plot encode and decode signal. We set N as quantization, so N equals to 3. Here Y is U encode, which is uniform encode. R equals to U decode, Y and 1. This coding is for figure 2. And here also we label X as time, Y as amplitude, and title as encoded signal. And then here we title as decoded signal. And then this is the last coding for the figure 3 output. This coding is for the square signal. We label X as time, Y as amplitude, and title as Y signal. So now I am going to show the output, this coding. We set the program and then run. So we get 3 outputs. This is figure 1 output, analog signal and sample signal. Here X is time and amplitude is as Y. Then figure 2, this is the output for the figure 2. This is the encoded signal and this is the decoded signal. And the third output is figure 3, and this is our square signal. Here X as time and Y is as amplitude. So for the example 1 coding, we get 3 types of outputs. Here are the outputs.
I'm Tan Jianhua, and I will explain for example 2. In example 2, we need to observe the received signal with and without compending, which is compressing and expanding the pulse code modulation signal. First of all, we need to clear and close everything and make the time metric 0 to 3 with increment 0.01. And the message signal, which is sine wave with parameter 2 pi t. Then we make variable c with function compend, and parameter x, mu value 255, and maximum value of message signal is 1, and mu compressor. Then we encoding the signal with function u encode with input signal c and quantization bit to 3. Then we decoding the signal with u decode function with parameter e and quantization bit. Then we expand the decode signal by accept variable of and expand again, which is input signal d, mu value 255, maximum value of message signal is 1, and mu expander. Next, we plotting the graph figure 1 and figure 2. And this is the output. That's all from me.
Good day, sir. My name is Tan Jia. So now I would like to present the 3.0 exercise. So in the first question, we will need to calculate the frequency of the analog signal in the code example 1. So we know that the signal equation is sine 2 pi t. From that, we know the angular frequency is 2 pi over t, that is 2 pi over 1. Then we will calculate the frequency from 1 over t. Then after calculate, we get 1 Hz.
In question 2, we will generate a 2K Hz sinusoid with peak-to-peak voltage of 2 volt and generate a quantized signal when n equals to x and 16 levels. Then we will calculate the signal to quantization noise ratio SQ and R. So for n equals to x levels, we will first calculate the quantization level, that's L equals to 2 to the power n. Then 2 to the power of x will be equal to 256. Then we will calculate the SQ and R in dB. That's 10 log 3 L squared over 2. After calculate, we will get the 49.93 dB. Then we will generate a 2K Hz sinusoid here using the MATLAB software. First, we will close and clear all the program. Then we will declare t with the time interval 0 to 0.0015 with the interval 0.00001, and the frequency here we will multiply with 2000, and n will be our quantizing level, that's x. Then before that, we will compressing and expanding our signal with the mu law compending command with the parameter of 255 and the maximum amplitude is 1. Then we will uniform encode our signal with number of bit with 8 and uniform decode our signal at the receiver side. Then we will expand the signal. Then we will plot the signal. We will also plot the PCM code without compending, that we just uniform encode our original signal and uniform decode our signal. also with n equals to 8 bit. Then we will plot the signal again. So when we run the code, we will get the signal, receive signal using compending here, and the receive signal without compending. For n equals to 16 levels, we will first calculate the quantization level L equals to 2 to the power of 16. Then we get 65,536. Then we calculate the SQNR in dB with 10 log 3 L squared over 2. Then we will get 98.09 decibel. Then we will generate the quantized sync level of 16 with the 2 kHz signal. And the same, we will use the mu-law compending, and we uniform encode and uniform decode. Then we will expand it. Then we will also plot the PCM without the compending. That's uniform encode and uniform decode our original signal. Then when we run the code, we'll get the quantized sync level of 16 of the signal here, and this one is without compending.
In question 3, we use the Simulink to the question 1 and question 2. So in question 1, we will design the PCM here. The signal generator, we use the sine wave with amplitude 1 and frequency 1 Hz, which is the same as the chord example 1. And the pulse chord generator is amplitude 1 and the period is 0.1. That means we will use a 10 Hz of this square wave, and the pulse wave is 50% of the period. Then we use a scope to analyze the signal of our message signal. Here, the dot product, we will use it to sample our signal, and then we will do the uniform encoder with 3 bits, and the peak value is 1. And the uniform decoder, the peak is 1 and the number of bits is 3. Then we will see the decoded signal here also. When we run it, we will get the decoded signal, same as the question. And the analog signal here, we can see that we use 1 second to take a complete 1 cycle here. That means it is 1 Hz.
Now we will do the Simulink for our question 2. So first we will generate a 2 kHz sinusoid. Then we will pass in the signal into our uniform encoder with 8 bits. That's our 8 quantized sync level. And we go to our uniform decoder with 8 bits also. Then we'll multiplex our quantized signal with our message signal, and we can observe the signal with our scope. So here is our signal, quantized signal without compending. And here our quantized signal with compending, we will generate a 2 kHz sinusoid. And then we will pass in the mu-law compressor with the mu value 255 with the peak amplitude of 1. Then we go to the uniform encoder with 8 bits and the uniform decoder with 8 bits also. Then we will expand our decoded signal at the receiver side with the mu value 255 and the peak amplitude is 1. Then we'll multiplex our signal, quantized signal with our message signal. Also, we will set our stop time to 0.001. When we run it, we will get our quantized signal with using compending and without compending. Next, we will do the quantizing level of 16. So we will just change the value of bits and the uniform encoder with 16 and the uniform decoder for the without depending quantized signal. And also our compending received signal here, we will change the uniform decoder into 16 bits and also the decoder into 16 bits. Then when we run it, we will get the quantized signals of quantizing level of 16. Here is the received signal using compending, and here is the received signal without compending. So from the result, we know that the received signal is highly correlated to the quantizing level. That's all from 3.0 exercise.
Very good evening. My name is Alan Sivalingam, and today I want to talk about the discussion. In discussion, we install the suitable toolbox such as the signal processing toolbox, communications toolbox, and DSP system toolbox in the software, which provide functions and apps and of analyze, pre-process, and extract features from uniformly and ununiformly sample signals. It also provides algorithm, apps, and scopes for designing, simulating, and analyzing signal processing system in MATLAB and Simulink. The frequency can be observed directly from the equation of sinoid signal, sine 2 pi t, whereby frequency is 1 Hz. In order to get more clearly and viewable waveform, set the interval from 0 to 0.0015 seconds with 0.00001 second per sample, which will generate 3 complete cycles of that signal.
For conclusion, a signal is pulse code modulated to convert analog information into a binary sequence, example like 1 second and 0 second. In pulse code modulation, the message signal is represented by the sequence of code pulses, and quantizing is a process of reducing the excessive bits and conversation data. The sample output, when given a quantizer, reduce the redundant bits and compress the value. Quantization noise is a model of quantization error introduced by quantization in the ADC. It is a rounding error between the analog input voltage to the ADC and the output digital value, and the noise is non-linear and the signal dependent. It can be modulated in a several different ways. That's all from me and from us. Thank you.